Okej, så vi vill visa följande tre, men jag tror jag kommer ta det här på engelska, min egen skull. Så let R be a ring. We want it to be a commutative ring with the unital element, multiplicative unital element, and ring, and let F in R. Then this statement holds. So that is what we want to show. Oops. That is our O here is the structure, or O sub spec of R is the structure sheaf associated with the affine scheme spec of R, and D of F is a principal, distinguished principal open subset, I guess you would call it. The claim is that this is isomorphic. I suppose we want to say isomorphic as a K algebra to no, not as K algebra, sorry. I think I wanted to only be isomorphic as a ring to R localized at the element F of R. So how do we show this? So we have the claim is, and I will not show this part, but the claim is that we have a well-defined map uh, which looks like this. So basically, it just acts as the identity on the elements of the localization of R at F. And so what we want to show, I will not show this is a ring homomorphism. I don't think it's that hard. I want to show that this is bijective. And the injective part is not that hard. What is much more involved is the surjective part. So I will show the injective part first, and if we have time, I'll show the surjective part. Okay. So injective and proof. So first at ring on well defined. Okay. Injective. Okay. So we want to say that if G quoted by F exponential to R is 0 in the structure sheaf at D of F, then this forces G of F of R to be 0 in the localization at F of R. So, okay. What can we say from this? Right? So, okay, so this means that we have some element phi, which equals G of F of R on G of F, right? So in particular, this means that since phi, this is by definition of the structure sheaf, looks like this, we have that this means that phi of P equals G quoted by F exponential to R in R localized at P. So this holds for every P, so for all P in D of F. So, okay, what can we say from this? I will sum out. bit. So, okay, so what can we say from this? So this means by definition, this part, or rather this part, means that by definition, there is some h not in P such that h of G equals 0 in R, right? And this holds for every P. So that means that the set J is such that it is not included in P. And this in turn means that the zero set of J is included in the zero set of F. So one can show that since this holds for every P, for all P in D of F, that's why, I won't show this here, I think, but that's why this holds. So that in turn by the Nullstellensatz gives us, so we go from here to here, Nullstellen. So Hilbert's Nullstellensatz gives us that this holds, right? What does this mean? Well, this means that since right, so let's see. Right, so that means that there exists some k natural number such that f exponential to k is in J, but by definition, J was this set, right? So this means that we have such a k such that f of k g equals 0 in R. But that means that this holds, right? This holds on, so let's say if I get this right. So this holds on G of F. Well, okay, let's see. I want to say that this holds in RP for all P in DF, right? Wait, sorry. No, so this in particular means, right, so this means that this holds in or localized at F, right? Because, I mean, it's looking at the denominator here. I'll get this right. Denominator, numerator, denominator is the low one. So that is what we wanted to show, right? So this, since this is really 0 in this localized ring. So that shows the injective part. So what remains is the surjective. So surjective. So that is for, so recall that the map was from the localized ring at F to this, right? To the structure sheaf at or spec of R at F. principal open set. Okay, so if we have some section here, S, it will look like this, right? Oops. And in particular, by definition of the structure sheaf of spec of R, or generated from an affine scheme, this means that for all P in D of F, there exists some open neighborhood U of P included in D of F. And here P is in U of P such that S, I think I want to call S phi. So I want to call this phi such that phi of, okay, so right, so phi equals G of P F of P on U of P. And okay, so by definition of the principal open sets, things on the form like this form a basis for the Zariski topology on the spectrum of a ring. So that means that some P's here, not necessarily all of them in D of F, but this holds, right? So that means that their P is in some D of H of P. And so we will call U of P now, from now on, D of H of P, right? So we make this identification. So we might be shrinking the neighborhood a little bit here because we still will have P in here. So, right, so okay. Let's see, what do we want to do now? So, okay, so now we have on the HP, and let's see. Right, so here, right, so here, okay, right, so notice that D of H of P is included in D of F, and this is equivalent, I claim, to this inclusion. Which in turn is equivalent to by the affine node Stellensatz. This means that so notice here the inclusion reversing nature of taking radicals here. So this means that this holds, right? And by definition, this means that there exists some natural number R such that HP of R equals C of F here, right? Where C is in R. And so from this, we note that, okay, sorry. So, Right, so there's a mistake I made here. Let me go back. So what is really true here, what I really want to say, so what I really want to say here is that g of h of p is included in d of f of p, and that's because this has to be non-zero on this neighborhood, right? Otherwise, this is not defined. And now I do the same thing I did here, but just exchange f for f sub p, and then we will get this instead. So I won't do that. It's the same procedure as I just did. So, and of course, this means that for some natural number r, we have this, right? And then it follows that these sets of equalities hold. And this one is because the primality of so we're looking at prime ideals in the ring R here. That's why this holds, because yeah, I won't explain why, but I claim that this equality holds because of that, mainly, or entirely, perhaps. I don't recall exactly. I don't think it's hard to show. And notice that this equals, right, which is included in d of f of p. So what we want to do now is we set, okay, first we notice that, okay, if we set d of h of p equal to d of f of p, so possibly doing some shrinking here, then we have on, from now on, we have on d of f of p, we have g sub p, or g sub p quoted by f of g sub p over f of p equals so let's say that equals c g sub p over h of r or p due to this fact. Okay, so right, so okay, we have this equality here. Let me go back and see what I want to say now. Okay, I think you want to claim now that from this it follows that I want to claim that. So the reason we did this is basically I think we want to say that these are equal and to identify them. And right, so I think the claim we want to make here is that on these sets we have that phi can be written just as this, right? Okay, and I think I got this mainly right. Maybe there's some detail here. I hope I didn't mess things up too much. But okay, so now, of course, we have this, right? We really have an equality here, but this is what is important. And this statement is equivalent to this, which is equal to this statement. And so from this statement, we get that by applying the Nullstellensatz again, I mean, we did it earlier, that this is included in this, right? And that means there exists some R natural number such that f of R is equal to some, this is important, some finite, so say L equal 1 to N, and then K P L F P L. So, and that shows really, one can show from this that it follows that we can cover D of F by a finite set of these principal open sets, right? And so from this, okay, so what we want to do now, I think, is look at intersections of, we take two different f sub p of L and f sub p of K, which are like, so we pick two different prime ideals from this finite set of ideals. If you think of them as like p of f up to p of 1 up to p of n here, coming from here. So of course we know that this equals f of p, f of q, and we know that we can write phi as g of p of here, g sub p, f sub p, but it is also equal on the intersection to g of q over f of q. So this holds on the intersection. And so, okay, so by injectivity of the map we exhibited earlier, this means that in R, f of p, f of q, these are equal, right? So, and what does it mean that they are equal? That means that exists some m natural number so that fp, fq exponentiated to m, gp, fq mean minus gq, fp equals 0. And if we now set gp equals to gp f of, let me see so I get this right, I think I want f of q, maybe f of p here, let me see, f of p, n, and f of p equals f of p, let me check my notes maybe, so I don't mess this up. Okay, I can find it there. Let me check here. Right. So right. So that one, let me see. Let me check again. Yeah, so that one is right, and I want to set this to n plus 1. Also, I guess you should notice that the principal opens here, or the principal opens of this is contained in this, and the same. These are actually, I claim, the same due to an earlier statement that I made. So, okay. So if we do this, then notice that okay, so a small point of digression that I failed to mention is that the n here, the n is the maximum of all the such m's we could find. So max of m1, call it m prime. Yeah, that's a bad. Let me see. So call it n prime. Yeah. So okay. So okay, I think the claim here is now that we will have that g of p over f of p equals g of p f of n of p and f of p n plus 1, right? So this holds on every d of f of p. And actually, yeah, right. So one shows that it follows that g of p f of q minus g of q f of p equals 0 for all f q in g of f. And if we now write f exponential to r as this sum that we found earlier, right? And we set so okay, so we set, let me just check, we set, okay, we set g equal to like this with the same piece. Then we have that g of f of q equals p k p gp f of q, and notice this part, this is equal to kp G of Q, F of Q, no, sorry, F of P, and we can now move out the G sub Q and get P, K, P, F of P, but this is equal to F of R, F exponential to R. So what we have found is that G F of Q equals G of Q F exponential to R, which is the same as saying that this holds, right? And okay, I think I want to claim that this, we show that this holds for R G of F of Q. So, right, so that means that, I think I want to claim that that means that this holds on G of F. Right? Right. So okay, right. So that means that this shows the surjectivity I claim, because then we just take the element G over F exponential by R in R localized at F, and this will get sent to G of F of R equals to phi in the ring of the structure sheaf at G of F. So we are done.